Welcome back to Statistical Methods. This is Week 7, Lecture 1, where I'll be covering one-sample t-tests. Now, up to this point, we've discussed hypothesis testing using fairly artificial examples where a hypothetical comparison population's mean and variance are known in advance. But in most real-world situations, we don't have this information about population parameters available to us. Instead, everything we know comes from the data we've actually collected. In other words, our sample. Now, it is still possible to test research hypotheses when we don't have this information about the true population parameters, but this will require us to utilize a new type of probability distribution known as the t-distribution. We will first learn how to use this distribution when our null comparison distribution, or in other words, our population distribution, has an unknown variance, or sigma squared, but a known mean, or mu. So imagine you volunteer for a local chapter of a charitable organization, and you see a published report stating that the average member in this organization, across all of the chapters, helped fundraise $200 in the previous year. Now you have a hunch that people in your local chapter raised more than this, and that's your research hypothesis. So you randomly sample 20 members from your local chapter and record how much they've raised in the last year, and you get a mean of $240. And the question you're asking here is, did people in your chapter fundraise significantly more than the general population? Now, in this example, you want to ask how likely your sample mean is to have come from a sampling distribution of means based on a null population with a known mean but unknown variance. This situation calls for a hypothesis test known as a one-sample t-test. Now note that this mirrors examples we saw previously when performing z-tests, with the only difference being that we no longer have information about the population variance, or the population standard deviation. Now this lack of information about population variance requires a few changes to the hypothesis testing procedure we learned earlier. Because we no longer know our population standard deviation, or sigma, we must estimate it based on the sample data we collect. And when sigma is estimated instead of known, our comparison distribution ends up being slightly different in shape. So it's no longer the standard normal distribution we worked with earlier. So what do we do in situations where we don't know the population variance or standard deviation in advance? Well, we use our sample variance, SD squared, to approximate the underlying null population variance, or sigma squared. Can we just assume that SD squared and sigma squared are the same? No. Simulation experiments have revealed that SD squared tends to underestimate sigma squared, making it a biased estimate of the true population variance. So how do we unbias this estimate? Or in other words, to make it slightly larger? Well, by making a minor change to the formula for SD squared, the sample variance, we get to S squared, which is an unbiased estimate of the population variance. This is the formula we knew before, which is a biased estimate of the population variance, or simply the sum of squared deviations divided by n, or the sample size. But to unbias this estimate and to make this estimate S squared slightly larger than SD squared, we divide the sum of squares, or the sum of the squared deviations, by n minus 1, or your sample size minus 1. So S squared is this unbiased estimate of the population variance, and the only tweak here is that we are changing the denominator from simply the sample size to the sample size minus 1. Now, the denominator in this formula for S squared, n minus 1, is known as the degrees of freedom, or the number of scores that are free to vary given a known statistic. So for example, I know a set of scores has a mean of 15, and I know that there are 3 scores. I also know that 2 of these scores are 10 and 15. Now, since I know these 3 pieces of information, the third score is no longer free to vary. It is only one possible value, which is 20, because 20 is the only number that when added to 10 and 15, and divided by 3, will equal 15. Thus, in this case, the degrees of freedom equals 2. 2 scores can vary, assuming a mean of 15, But given that, the less score can only take on one value, which is 20. Now, the formula for degrees of freedom is, again, n minus 1, your sample size minus 1. Thus, the formula for s squared can be written more simply as sum of squares divided by df, or degrees of freedom, with that df being equivalent to n minus 1. Now, you might ask, does df always equal n minus 1? Well, for a one sample t-test, yes. But for other tests we're going to learn later on, no. So once we estimate the population variance with s squared, or the sum of squares divided by n minus 1, we can determine the characteristics of our comparison distribution, or the sampling distribution of means. Similarly to before, we just replace sigma with s. Now, the mean of the sampling distribution of means is actually equivalent to the population mean. So that's unchanged from before. So no work to be done there. Now, the estimate of the variance of the sampling distribution of means, that is the unbiased estimate of the population variance, is the unbiased estimate of the population variance divided by sample size. So that is, again, s squared, which we calculated earlier, the sum of squares divided by n minus 1, divided by the sample size. So that's how we get to our estimate of variance for the sampling distribution of means for a one sample t-test. Now, using what we calculate here, we can find the estimate of the standard error of the mean, which is again the standard deviation of the sampling distribution of means, simply by taking the square root of what we find here. So you can see that right here. Just remember the relationship between standard deviation and variance. Variance is the standard deviation squared, thus the standard deviation of the sampling distribution of means is the variance of the sampling distribution of means with a radical over it. Another way you could calculate this is by the standard deviation, the unbiased estimate of population standard deviation, divided by radical n. But for the sake of this class, we'll typically stick with this here. But note that this means you have two options for carrying out the square root part of this operation. You can find s squared, take the square root to get s, then simply plug it into this formula, or find s squared, plug it into this formula, and then take the square root of that to get the standard error of the mean, or the standard deviation of the sampling distribution of means. Just make sure you're not taking the square root twice in this process. Now, to summarize what we've covered so far, for a z-test, we have a known population mean and standard deviation, and the mean of the sampling distribution of means and the standard deviation of the sampling distribution of means, or the standard error, are calculated based on these known population parameters. Now, for a one sample t-test, the population mean is known, but the population standard deviation is unknown. And the variance and the standard error of the mean pertaining to that sampling distribution of means are both calculated based on these estimates. Such as the estimate of population variance, or sum of squares divided by n minus 1. Now, since our probability distribution is now based on an estimated as opposed to known population variance, it ends up looking a bit different than the standard normal distribution we relied upon up until this point. The sampling distribution of means based on an estimated population variance, or that statistic s squared, which is our unbiased estimate, is known as the t-distribution. Now, because this distribution is based on an estimated as opposed to true population variance, there is more room for error. Thus, we would expect there to be slightly more variability in means than in an exact normal curve. And the smaller the sample size and the degrees of freedom, the bigger this tendency is. So with a smaller sample size, S squared is based on less information, thus there's more room for error and variability. So the overall effect on the distribution's shape is that we end up with a slightly more spread out version of the standard normal curve, with the amount of spread dependent on the sample size, or in other words, the degrees of freedom sample size minus 1. And you can see that visually here. With lower DF, it's more spread out and more different from the normal curve. Look at this closely dotted line on the bottom. And with a larger sample size, it approaches the normal curve more closely. You can see that in this larger dotted line here. And this thick black line here is the normal distribution overlaid. Now, because of this greater spread, it makes more extreme scores to be able to reject the null hypothesis, or rather, it takes more extreme scores to be able to reject the null hypothesis in a t-distribution as compared to a standard normal distribution. So cutoff scores will tend to be more extreme for this distribution than they were for the standard normal. Thus, when you're using a t-distribution and you know less about the population, it's somewhat harder to reject the null. Now, to calculate a t-score, you'll need 3 pieces of information. One is the sample mean. You'll need the mean of the sampling distribution of means, and the estimate of the standard error of the mean, which is, again, the standard deviation of the sampling distribution of means. So here's your formula. T equals your sample mean minus the mean of the sampling distribution of means, which is the same as the population standard deviation, or rather population mean, and finally the standard error of the mean. Which is S squared with a radical over it. So square root of S squared. Now, note that this is analogous to the 3 pieces of information we used to calculate z-scores. We needed our sampling mean, the mean of the sampling distribution of means, and the variability of the sampling distribution of means, which was the standard error of the mean. Now, when we're dealing with t-score cutoffs, option 1 is to use the table in your textbook. The degrees of freedom are in the leftmost column, and it provides cutoff values for p equals 0.01, p equals 0.05, and p equals 0.01 for both one-tailed and two-tailed tests, which work in the same way as they did with z-scores and z-tests. But option 2, which is the easier option, which I suggest you use, is the Students T-Distribution Shiny app, which can be found at this link. And it's similar to the standard normal curve Shiny app in terms of how it functions. For inputs, you choose either the probability, the p-value you're looking for, or the t-scores, the starting point. You enter your degrees of freedom, whether you're using a one-tailed lower or one-tailed upper or two-tailed test. And you enter or slide to enter the value of p or t that you're interested in, and then it will return the alternative. Now note that t-scores like z-scores can also be positive or negative based on whether the sample mean is higher or lower than the sampling distribution or population mean. And also note, as was stated earlier, that as degrees of freedom increases, cutoff values decrease. So there's less error and more truth in the estimate of the variance with larger samples. Thus, it becomes easier to find a p less than 0.05 and reject the null hypothesis with larger sample sizes. And this is always going to be the case. So I'll end this lecture with a in-class problem. You have an aquarium of goldfish and want to know whether your goldfish are smaller than the general population of goldfish. You look up information about goldfish and find that the general population of goldfish has a population mean of 4 inches. Unfortunately, there is no information about the standard deviation at the population level available. But your sample of 10 goldfish has a length of 3.5 inches on average. So that's your sample mean. And a sum of squares of 6.4. So I want you to tell me how many degrees of freedom there are for your sample of goldfish. And again, this will be based on your sample size. What is the estimate of the population variance based on your sample data? So that is S squared. Just look back in the slides to find the formula. What is the mean of the sampling distribution of means? And this is somewhat easy. It should be the same as the population. What is the estimate of the variance of the sampling distribution of means? Or in other words, what is S squared of M? And finally, what is the standard error of the mean, or the standard deviation of the sampling distribution of means? You could look back earlier in the slides to find formulas here. And you could pause the video here to complete this. Because on this page, I have the answers. Now, please reach out if you have any questions with this information. It can be somewhat tricky, but I, based on how you guys did with z-scores and z-tests, imagine that you'll do pretty well. Not much is changing here. The only difference is we don't know our population standard deviation or variance, and we have to make it to a few tweaks to go through with our test statistic on account of that. Well, I'll see you next lecture.